thanks for inviting me. I have to say that when Mooney invited me, I was a bit surprised because I haven't really been working in PCPs or interactive proofs in a long time. And so, but then we talked about what I talk about, and it's going to be like a senior citizen talk. It's going to be a history talk. And it's okay. So it's going to be a linearity testing, lots of stories, how we got to the problem, how we approached the problem, and there are many ways, and what happened a bit after. And then at some point, I'm going to have to leave off to the recent work to the next talks tomorrow. So I want to say this work, I wanted to sort of dedicate it to sort of the young people in the room in the sense that just to have a sense of what it was like to be young. I still remember, I think this is one of the few things I still remember. And it's also dedicated to the old people in the room in the sense that I'm not going to do anything technical or hard. So so hopefully there's something for everybody. Okay. All right, so I should apologize. These stories, they're not entirely true. They're not complete. It's not chronological. I'm sure I messed up references. But I will, even though I messed up my own references, I will take my chance to pick on Guy for messing up his references. And so that's revenge. Okay, so some context. So I want to start with the context of where things were. 1987, end of the Cold War, okay? In America, we were learning a lot of Russian words. Okay, some of these you may recognize. And some of these, were specific to the time. And I'm not going to try to pronounce these because you'll make fun of me. So, but there was this one proverb, this one here, that we kept hearing. And what was that? So there was, at the time, in 1987, there was the INF Treaty, okay, between two arch rivals, the USSR and the United States. They, were main enemies. There was the very end of the Cold War, and they were about to sign an arms control treaty. Okay, so how do you believe that you can reduce your nuclear arsenal if your enemy is just saying they're reducing their nuclear arsenal? How can you take this chance that you should trust them? So the proverb, this proverb here, apparently means trust but check. And that was sort of the guidelines and the sort of surrounding theory of this treaty, this INF treaty that was so famous. So we were hearing trust but check all the time. Okay, so that's 1987 in the news. 1988 in Berkeley. Okay, I'm a PhD student. It's a tough time out there, not clear where this is going. And look at who the other PhD students were. Okay, so this was like, wow. Okay, so it really wasn't clear what, the job market in theory was really tight. There were really no jobs back then, not like now when we just say there are no jobs, but there really weren't any jobs back then. And so here's a conversation that never exactly happened as a conversation, but all of these statements were made. Okay, so it crossed my mind that I should have a plan B. I should have a plan B. And Manuel said, well, why don't you work on program checking? Okay, what's program checking? So here's what's program checking. Okay, when you run a program, how do you know that the program didn't make an error? Well, trust but check, just like the INF Treaty. Okay, and this was the guiding principle of program result checking. But what was beautiful about this model was you can use the program to help you check. Okay, so this was the interesting thing about the Blumkin model. And in particular, you can call the program on other inputs, not just the input that you care about. Okay, so here is the model of Blumkin more formally. You're given a program P. You can make as many calls to it as you like. It's claiming that it's computing a function f. And you're also given a particular input x for which you care about the answer. Okay? Now, what we need from the checker is if the program is correct on all inputs, in particular on the input that you care about, input x, then this checker should not invent a problem, okay? So you should output pass. Also, if the program is incorrect on the input that you care about, x, then that checker should output fail, okay? And all these with high probability. Okay, we don't specify what happens. Maybe the program's correct on input x, but incorrect on some other input. Then whatever you answer is progress, okay? So either way, science wins because either you you found an error in the program, or you know that the program is correct on input X, which is the input that you care about. Okay, so either way, you made some kind of progress. All right, so that's what we want from the checker, but how do you check the checker? How do you know the checker is correct? Well, what they asked is that the checker should do something other than computing the function f, okay? And in particular, what we want, well, what does it mean different? We want the checker to be different than computing the function. We have no way of specifying mathematically what it means to be different. So the way that Blumkin said to enforce this is demand that the runtime of the checker be little o of the runtime of the best program for the function f, okay? So this was the definition, and it met with, some people went ballistic when they heard it, okay? Because we did not have fine-grained complexity back then, and especially people that had a logician background, they went crazy. They're like, what do you mean? This is not a definition. This is just not a definition, because what do you mean better than the best run program for a function f? What if you get a better program? So remember at the time, this was when the matrix multiplication exponent, remember in the mid-'80s, the matrix multiplication exponent was going down every day. and it was, so they were like, no way, this is a terrible definition. And still, it turned out, I claim, to be a great idea, because it did, if you look at the checkers that were developed in this model, I think, at least I think, and I think you would even agree, they were doing something other than computing the function. They were very different, and they led to interesting ideas. So sometimes adding a weird constraint is all you need, okay? So scientifically, it was a great idea. Mathematically or logically, maybe it's not the best definition, but it worked great. Okay, so examples from Blumkin. They had some examples for sorting, multi-set inequality, extended GCD. That's when you get the coefficients that help you check. Like that's the program not only outputs the GCD, but also the coefficients that help you check that that's the right GCD. Okay, but what they also had were some really interesting examples of checkers that were via the ideas of interactive proofs. Okay, so they showed graph isomorphism. So this was sort of really following the graph isomorphism interactive proofs, the graph isomorphism, graph non-isomorphism. They also had a group theoretic interactive proofs for canonical element, group intersection, and equivalent search. Okay, so, but then there was also for matrix rank, and that also looked like a PCP. And what was interesting, I mean, like an interactive proof, and what was interesting is it's an interactive proof for a problem in P. In fact, a very easy problem in P. So let's say, so I think this was cool. So I decided that you're going to have to see this. So I'm going to show it to you. Okay, so here's an interactive proof for the matrix rank of a big matrix A, an n by n matrix A. And let's say the program claims the rank is R. Okay, so the overview of what we're going to do here is we're going to use calls to the program to find an R by R submatrix B supposedly of full rank. Okay, so how are we going to do that? We're just going to call the program without one of the row. I mean, we're just going to go row by row and try to delete the row and see, does this remaining matrix still have rank R? And if it still has rank R, well, keep the row deleted, just throw it in the trash, okay? And if it no longer has rank R, if it went down to rank R minus 1, put the row back. Okay, so that's the plan. We're going to keep doing this. We're going to run through all the rows, see which ones we can throw out, and then at the end, we should end up with only R rows, and then do the same thing for the columns until we get an R by R matrix that remains. And everything would have been great if we could trust that the program never lied to us, but we don't know. Okay, so so we've got this B. What we're going to do next is check that the rank of A is at least R by checking that this matrix B that we ended up with is of full rank. And then we're going to also check that the rank of A is at most R. Okay, so I'm going to say more about checking that B. On the next slide, I'm going to say more about checking that B is of full rank. But this checking that rank of A is at most R, I'm not going to talk about because I'm just going to tell you it's similar ideas to what I'm going to talk about in the next slide. Okay. All right, so here's the idea for checking that matrix B is of full rank, and you're going to see it looks really just like an interactive, just like the usual old interactive proofs that you've seen for harder problems. For each row J, what we're going to do is pick a random 0, 1 vector, and what we're going to do is replace that row J by a random linear combination of the rows of B. And the random linear combination is going to be determined by these coefficients, these C1 through CR. Okay? Now, ask the program what the rank of this new B is with the replacement. And if the rank of B is R, then the rank of B, the new B, is going to be R if Cj is equal to 1, and it's going to be R minus 1 if the coefficient corresponding to the jth row is 0. Okay, so you ask the program, and you should get J if Cj was 1. I'm sorry, you should get R if Cj is 1. You should get R minus 1 if Cj is equal to 0. And the point is, a correct program would know. Like, a correct program would know the answer and would be able to give you the right answer. An incorrect program that's trying to fool you needs to know if this new B came from a heads or a tails, like came from a Cj equals 1 or a Cj equals 0. The problem is, if J is actually not independent of the other rows, then this new B distribution is indistinguishable in the two cases. And that's why the prover is not going to be able to fool you with probability more than a half. So it really looks just like an interactive proof. OK, great. So this is an interactive proof. OK, I wasn't the only one that was excited by this. Neither were Blumkin and Kanan. Len Edelman came to visit Manuel, and he saw this, and he got excited. So Edelman, Huang, and Campella came back with this really cool checker for GCD, which I'm also going to show you. So this is GCD that's not extended. So nobody told us the coefficients that allow you to check that this is the right GCD. So now this GCD, let's, without loss of generality, say that the program tells you the GCD of A and B is 1. Okay? I mean, if they say something else, then divide by that number, and you've reduced to this case. And not only that, without loss of generality, oh, OK, so now, OK, so it says the GCD of A and B is 1. Now, I can check myself, like if A and B were both even, I would know the program is lying, right? So let's assume it's not even. So in fact, let's assume that there are no small multiples of A and B, because you can just test by yourself. Test all the numbers between 0 and 100 and make sure that A and B are not divisible by small numbers. Okay? So either the GCD is really 1, or the program's lying, but if it's lying, it's something bigger than 100. Okay? All right, so here's the checker. And I'm kind of giving you an approximation to the checker, because I don't want to show you every little detail of the probability distributions. But the idea of it is, pick some random numbers, y1, y2, y3. And then, OK, so these are just arbitrary random numbers. And these are usually not multiples of G. Why? Because they're big. I mean, because G is big. And I'm just picking these randomly. So what's the probability that G is bigger than 100? The probability these three are multiples of G, pretty small. OK, but now we want to pick 3 random multiples of G, random and independent of each other. Each one of these, the way we'll pick it is we'll pick a random number, r sub I, and set xi to be r sub I times a mod b times 2 to the j. OK, so if the GCD of A and B is G, then this thing can only give you multiples of G. OK, but in fact, it turns out that Edelman, Huang, and Campella showed that this gives you a random multiple of G in the range 0 to b times 2 to the j. Okay, so if G is 1, then it's just a random number between 0 to b times 2 to the j. But if G is big, then it's really giving you a random number only on multiples of G in that range. Okay? Now, again, let's assume we're in the good case, that the y's and the r's are all relatively prime. Okay, the y's are not multiples of G, and the y's and the r's are all relatively prime. Let's assume that that case happens often enough that let's just assume we're in that case. Okay? Because if the prover is going to cheat, because this case happens with constant probability, if the prover is going to cheat, it has to get this case right too. Okay? It can't just be right when this doesn't happen. Okay. So now, here's what you're going to do. You're going to flip a coin, and if you toss heads, you're going to ask the program, what's the GCD of x1 times y3 and x2 times y3? Now, you think it should be y3. So you expect to get that. But what's the real answer? Well, if G is not equal to 1, then each of x1 and x2, they're multiples of G. They're random multiples of G. So it's really, the real GCD is G times y3. Okay? the real answer is g times y3. You expect y3. The program has to cheat. It has to cheat if it's going to convince you that the GCD is just 1. Okay? Now, if you flip tails, then you ask the program, what's the GCD of x3 times y1 and x3 times y2? Now here, you expect the GCD to be x3. Okay, in fact, it will be. The real answer is x3 too. And in this case, the program must tell the truth. Okay? So in this case, if you flip heads, the program has to cheat. If you flip tails, the program must tell the truth. Well, maybe the program can tell the difference from looking at these numbers that it got, whether you flipped heads or tails. But look what's happening here. In both cases, what do these inputs look like? You have x1, which is, it's a random multiple of g. Okay, so it's some random number times g. And then times y3, which is another random number. Okay? And here you have x2, which is a different random multiple of g, but independent, times another random number. So in both cases, you have a random number times g times a random number. And here, what do you have here? x3 is a random multiple of g. Okay, and these guys are independent because x1 and x2 are independent. Here, you have a random number times g times a random number also. But these guys are independent because y1 and y2 are independent. So basically, these two distributions are similar enough that the program cannot tell the difference. It's going to have to make a choice, okay? And you can catch it. All right, so this is the idea behind the GCD checker. It was a really beautiful idea, and it was so cool to have an interactive proof for something that's so easy. So it would never be you would never think of looking for back then. You would never have thought about looking for an interactive proof for a problem that's so low level, because back then we thought of interactive proofs as things for hard problems that we're basing our cryptographic functions on. So this was sort of a new idea, and this was my reaction. Wow, that's really cool. Okay, so I really liked their analysis. It was very beautiful. But it seemed every time they got a new checker for a new problem, it seemed, okay, that's the last one. Okay, okay, good. You found another checker, but that's it. Now there's no more interesting checkers. And it was really hard to think about what's the next problem to look at. Okay, but everybody back then was talking about parallel computation. Everybody was interested in the PRAM and this and that on the PRAM and NC0 and AC0 and NC1 and NC2 and AC, all those things. We were talking about it all the time. So I said, what about parallel checkers? And so did my office mate, Sampath Kanat. It was like something in the air. It was like the obvious next step, think about parallel checkers, okay? So we both thought about it separately. And here, it's the same idea for a checker. You still want, it's the same basic notion. If the program is correct, you should output pass. And if the program is incorrect on the input that you care about, the checker should output fail. So that's the same. And also it's the same that the checker should be different than actually computing the function. But how do we enforce it now? Now you can talk about the parallel depth of the checker being little o of the depth of the best program for f. Okay, this is just like before, but what's different is we actually had lower bounds on depth. Okay, so we actually knew that there were functions you couldn't compute in AC0. So there was a hope of having a checker that's provably different than the program. Okay, so that was the idea. And in fact, here's some examples of parallel checkers. You could get things for, this is problem by problem, all pairs shortest path, max matching, sorting, even some, back then people had to know everything, right? So we even had to pretend we know something about computational geometry, dynamic programming. And what was nice, you could even parity was something you couldn't do in constant depth, and you could get a checker for parity. Okay, so what about multiplication? So given A and B, and I'm going to write them as this is the highest order bit of B and the lowest order bit of B, here's a simple checker for multiplication. Okay, so so we're multiplying A times B, and I'm just going to write B in this bit by bit. And let's let bi be the suffix, starting at bit I down to bit 0. And now for all I, what we're going to check is that the program's value, when it multiplies A times B sub I, is consistent with the program's output on A times B sub I minus 1. Okay? So, what does it mean? We just look at one more bit of B. And so if the next bit of B, if B sub I Oh, that's a bad notation. You know, this is what happens the first time you give a talk. So sorry about that. So let's call that bi hat or something. If b sub I is actually 0, then the program's value on the first I bits, the lowest order of I bits, and the program's value on the lowest order I minus 1 bits of b should be identical, okay, because it's actually the same number. So if bi equals 0, then these two should be the same. If bi equals 1, then actually you should add another value of a shifted over, a plus 2 to the I. Okay, look at this. This is something we can compute in constant depth because you can shift. You know, you can't do general multiplies, maybe, because that's as hard as the original problem, but shifting is just to pad by I zeros. We can do that in constant depth. And adding is something we can do in constant depth. Okay, so this is a constant depth checker. The total number of processors is at least n squared because it's n times the number of the times to set up all these things. Okay, so that's the checking number of processors. All right, so now there's a question, could you do better on processors? Well, okay, so now comes the part. So let's talk about a self-testing, self-correcting paradigm with Blum and Luby. What is self-correcting? This is essentially, you know, this is really nothing more than using random self-reducibility. This was also found independently by Dick Lipton. Here, you're given a program that's correct on most inputs, and we talked about it this morning, but I'm going to give you more details. And the idea is you need to fix it. So let's talk about what the self-corrector would look like for multiplication. And, you know, multiplication has 2 inputs. I just want 1 input. So let's say you're always multiplying by a fixed constant b. Okay, so b doesn't change. All right, so we're given an input x. I want to compute x times b. The program computes x times b, but I don't know if the program's right on x. It might be, it's wrong on most x, but it might not be wrong on the x that I care about. So we can generate a random y, call the program on y, call the program on x plus y, and output p of x plus y minus p of y. Okay, so with high probability, it's correct on both x plus y times b and y times b. I subtract, I should get back y x times b. Okay, so that's what I should get just by the linearity of multiplication. Okay, so if I had a program that was known to be correct on most inputs, I could turn it into a program that's correct on every input with high probability, assuming that you know, if this wasn't high probability enough, I'll repeat for many y's and take the majority answer. Okay, questions? All right, so how do we know it's correct on most inputs? Self-testing. Okay, what is it? You should pass good programs, and you should fail programs that are wrong on a large enough fraction of the inputs. Okay. And again, this little o property, you should do something other than compute the function. So this is the same. But how would you construct it? Well, you could use a checker if you had one, but we're trying to write a self-tester to construct a checker, so it's kind of the wrong direction. So what are the other methods for making a tester? And I'm going to mention a method that Guy talked about earlier, and I'm going to sort of edit the references. So, okay. So the references are BLR. and here, I want to build a self-correct. So we have, what we're going to do is we're going to bootstrap. Okay, we're going to test programs of size 1. We're going to use it to test programs of size 2. We're going to use that to test programs of size 4, and that to test programs of size 8, up and to 2 to the I. And we'll do this log n times until we've tested programs that work on inputs of size n. Okay, so that's the plan. Okay, we're going to use the fact that we have a self-corrector. So we are assuming that the function is both random self-reducible, that gives us a self-corrector, and something I'll call downward self-reducible, which means you can write the function in terms of inputs that are much smaller. Okay? So you can, okay. So now, if it's random self-reducible, we can use the self-corrector that we had on the previous slide. And I'm assuming we had a program that's correct on most inputs of size n. Then via random self-reducibility, this transforms the program into a program that's correct on all inputs of size n. So we took a program, you know, that we'd have already tested on inputs of size n, and using self-correction, we turned it into a program that we can just pretty much assume gives us the right answer all the time. Okay, so this is just following from the previous slide. There's nothing happening here. Okay, this is the bootstrap tester. What it does is we are now going to test that the program is correct on most inputs of size 2n. Okay, we had something that was correct on most inputs of size n. We're moving up to twice as big. Okay, so we're going to pick random inputs of size 2n, and we're going to write the multiplication in terms of multiplications on inputs of size n. Okay, so we're going to cut the problem in size in half. This is a linear time reduction. Okay, and what do I mean by this? Again, for simplicity, let's assume we're just multiplying by b, because I don't want to cut both sides. We'll take the low order bits of a times b, plus the high order bits of a times b times 2 to the n. Okay, so that's all that is. Okay, so now these are both. This is a problem of size n. This is a problem of size n. And then later I take this answer and shift it by n. I can do that in linear time, right? Okay, so we've got this in terms of shifting. And now we will call the self-corrected program on these two multiplications and get the right answer for both of them, okay, with high probability. And then, so what we'll just do is just keep testing different random inputs of size 2n until we're pretty certain that even on size 2n, most of the inputs are getting the right answer. Okay? So we call this a bootstrap self-tester. And you can just bootstrap all the way up from size 1 up to size n in log n different levels. But since it's actually pretty efficient because the levels are doubling at each. So you spend you spend order n plus order n over 2 plus order n over 4. So that works out to order n. So the whole thing is pretty efficient. I should mention this algorithmic idea was independently used by Edelman, Huang, and Campella to check RSA. And with this idea, the bootstrap self-tester was used by Nissan on the permanent because there was the result of Beaver-Feigenbaum that said that any multivariate polynomial is random self-reducible. So the permanent is random self-reducible. And then he noted that the permanent is also downward self-reducible because you can write a permanent of an n by n matrix in terms of a bunch of permanents of n minus 1 by n minus 1 matrices. So he used this method to get a checker for the permanent. And that was the email precursor to LFKN. Okay. All right, so good. So we have a bootstrap self-tester and self-corrector. It's constant depth. Total processors for integer multiplication turns out to be order n. For modular multiplication, you didn't get it doesn't get smaller at each phase. So, and you need log n phases. So that was n log n. Okay, so can we do better on processors? So I'm still thinking in parallel complexity somehow. And then, well, are you kidding me? Like, who cares? This is we're just saving a log n factor on processors. Everybody tells you do not work on saving log n things. Work on important problems, not saving log n a factors, okay? And even Avi today was apologizing for works that saved order n factors. Remember he had that slide with saving order n factors? So this is just log n, okay? That's all we're saving here. And then, there was always in my mind, Oded Goldreich always has this story about Franco Pepperada complaining about why people are saving log n factors, and he, in some program committee meeting, went, just take the log n factor and do it like a human being. And there I was, saving log n factors. Okay, well, there was a reason to save a log n factor, which is actually, if you could save the log n factor, then you would get the little O property for integer multiplication sequential. Actually, this already gets in, sorry, it should be modular multiplication. So for integer multiplication, we already had the little o property because it was order n. But for modular multiplication, we did not have the little o property when you considered it sequentially. And this allowed you to get a sequential checker with the little o property. Okay, that was the only reason to think about this. Okay, so can we do better? Well, multiplication satisfies linearity. It satisfies for all xy, f of x plus f of y equals f of x plus y. Again, remember, I'm just multiplying by b right now to keep things simple. So this satisfies linearity. So can we test this linearity thing by picking random xy, test f of x plus f of y equals f of x plus y? Okay, can we do that? Well, this would not be enough because all linear functions satisfy linearity. The all zero function satisfies linearity. So you have to test that it's the right linear function. But that's not a big deal because you could just pick a random x and compare f of x and f of x plus 1 and make sure the slope's okay. So that's okay. All right? So let's get back to this linearity problem. And what I want to talk to you about is like the first idea for a proof. So there are lots of proofs for linearity testing. Most of you have seen one, maybe two. So I just want to claim there are more. Okay, so this is the first idea. So the first idea was to define a distribution D. Here's the distribution. Pick a random number, z, let's call it z, and output f of z. That's a distribution. Okay? So the distribution of the right-hand side is just this d, right? Because x plus y is random, and it's really just d. That's what the distribution of the right. What's the distribution of the left-hand side? It's sums of two elements chosen according to d. So this d convolved with d is just you pick two elements from d, sum them, and output the sum. Okay? So the right-hand side is d, the left-hand side is d convolved with d, but when you do this test, you're essentially testing. I mean, the only way this test can pass is if d is close to d convolved with d. Okay, so it's fairly easy to see this, that because every time you get something on the left-hand side, you have to also get it on the right-hand side. So it's saying that, okay, every time you see something on the left-hand side, you see it at least the same number of times on the right-hand side. So it's roughly, the only way you can really pass this test is if these guys are close. So maybe you should look at this question. So first of all, when is d equal to d convolved with d? And this was a studied question. You can look, for example, at the book of Diaconis. And this depends on the domain. So over like infinite cyclic groups, like integers starting at 0, then it has to be that d puts all of its probability on 0. All, okay? Over a finite cyclic group, then d has to be uniform over some subgroup. So, if you're like integers mod 10, then it's okay to put all your probability on 0, or, be uniform over multiples of 2, or be uniform over multiples of 5, or just be uniform. All of those are okay. Okay? So now the question is, when is d close to d convolved with d? What does that tell you about the distribution? Well, it turns out that you can show that d has to put all, just like before, but almost. D has to put almost all its probability on 0. And for the finite cyclic group, d has to be close to uniform over a subgroup. Okay, so in BLR, we showed it this way. And that was the starting point for the original proof of the linearity test in BLR. And then there was a further combinatorial argument that proved the linearity test. And it's kind of lost to the world. I mean, I have like half the manuscript. I can still find that, but I can't find the rest. So the good news is, there's some good news. I told you it's a comedy, but there are errors. This is an error. Okay, so we had this proof of the linearity test. It was kind of long and complicated, but then what happens is I was on an IBM Fellowship, and they made the people on IBM Fellowships go visit IBM. So I went to visit IBM, and they asked, what are you working on? And finally, I had something to say to that answer. So I asked them, if this thing is known, is it known that d is close to d convolved with d? Can you say something about the types of distributions? Okay, so they said, interesting question, let's talk. And then this is something that doesn't happen anymore. Some of you may not know what this is. This is a letter on paper. And when you're like a young grad student and you get a letter on paper from somebody you just met, like Don Coppersmith, and you're like, wow, okay, this was really made me happy. So he sent me this letter essentially saying that they have, not only have they resolved it, but they have pretty much the optimal parameters, because it's like classic Don Coppersmith. He always gets as close as possible to the best parameters, and there he did. And it was fantastic. This was, okay, so this already was interesting because it was really exciting that somebody cared. And then it got another email. Okay, so soon after that letter, we got another email with a much simpler algebraic method proof. Okay, and that's the one that's written in BLR. He allowed us to use that in the manuscript of BLR, and that's the one that's written. It's attributed to him if you look at the paper. So this is what we wrote, and also in that paper of BLR, we promised but this is a promise that took us 14 years to fulfill. We promised that we would write some extra things like what to do in the commutative case and blah, blah, blah. Okay, so we did it, but 14 years later. But I want to say that this proof here, although it's not the one that most people teach, this algebraic probabilistic method proof, it is the one that inspired the proof of the degree tester in later work with Sudan. So I think it's a really nice proof. And I often use it as an example when I teach class of probabilistic proofs. Okay. Okay, so why is this at all? I'm just going to try to give you a little bit of a sense of why linearity testing and convolution of distributions has anything to do with each other. And so there's a proof in this 14 years later paper that linearity testing, the efficiency of the linearity test is actually directly related to this convolution question. So in particular, if you have some proof of this convolution question, this is not the best way, by the way, to get a linearity tester. So this is really only for if you're interested. If you're not, blank out for a couple slides and I'll get back to other things. But this is it does not do better. But if you can show something like the distance between A convolved with A and A is at most beta, then A is some function phi of beta close to uniform over a subgroup, then that would tell you something about linearity testing. It would tell you that if delta is your error probability in the linearity test, then F is the same phi of delta close to homomorphism. Okay, so whatever you get for this thing, you get the same phi relationship here. Okay, so you can actually show this, and you can do it by considering, how much time do I have? 20 minutes? Okay. All right, so maybe I'll just say this, because I don't know how to, but okay. So consider the distribution P on pairs of elements. Now we have a distribution on pairs of elements, x, y, and we're going to give the probability of the tuple. This is, the probability of this pair is going to be 1 over the domain size if y is equal to f of x and 0 otherwise. Okay? So the distribution between P and P convolved with P turns out to be, if you think about this, it doesn't take too much time to think about this, but it turns out to be exactly the error probability of the linearity test. Okay? So assume your linearity test passes with high probability, then so this error probability is small, that means this distance is small, and that means via the theorem that we're assuming that F is uniform over a subgroup. Like we assumed that we have a theorem saying that if the distance between P and P convolved with P is small, then we're close to uniform over a subgroup. So this is the theorem we're assuming. And then if you look at the structure of this domain, like what it means to be a subgroup, like what is a subgroup of pairs x, y, it turns out that F has to be close to a homomorphism. Okay, and that's a connection. All right, so let me say more on testing. So this question of like when can for all statements be replaced by for most statements seemed like an interesting direction to continue. So we had linearity testing for all x, y equals f of x plus f of y equals f of x plus y. We had similar things for degree tests. You know, we had all kinds of different degree test formulations based on for all statements. And the question is, when can you take that for all and just change it into a for most? Okay, so there I was now a postdoc in Hebrew University, and I asked Nati, what other types of functions can be defined by these for all statements? And he said there's a whole field of functional equations, and in fact there's some books in the library, go. So I went. Okay, I mean Nati tells me to do something, I do it. Okay, sometimes. Okay, but this time I did it, and I'm glad I did. So I went to the library, like he said, and there are really whole books on functional equations, and essentially what they have are these statements that say for all x1 through xn, and then they have, you know, it wouldn't be for all x1 through xn, but some of these might be dependent on each other. So for example, in the linearity test, it'd be for all x1, x2, x3, but x3 has to be of the form x1 plus x2. Okay? In degree tests, they had different neighborhoods. So these neighborhoods are subsets of the domain, and these are like tuples of inputs that you care about. And what you do in functional equations is look at the function value at these different xi's, and then there's some capital F that you compute. these guys. Okay, so in linearity test, we'd have f of x1, f of x2, f of x3 is equal to x1 plus x2. And then we'd say, OK, the first one plus the second one has to equal the third one. Okay, and that's, and you know, if you move everything to one side of the equation, you get an equals 0. All right, so the question, which of these functions, and there were lots, there are books of these things, which functional equations are useful for self-correcting? Which functional equations lead to good self-testers? And in particular, what do I mean by lead to good self-testers? Essentially, we were asking, can you replace this for all statement by for most and still characterize exactly the same family of functions? OK, so here's some examples. And these are called addition theorems. They relate x plus y, x, and y, the function value at these places. And these are some examples. For example, this really weird one here, the solution to this is the cosine functions, you know, with different a's in front of the x here. OK? All right, so those are functional equations. There's more. Some of them relate x plus y, x minus y, x and y. And these are just the simpler ones. These are actually the ones we can turn into, some of these we can turn into self-testers. And there's much, much more. OK, so not all of these functional equations are good for testing. Here's a functional equation. OK, and this defines a class of functions, all the f which look like x plus c for some c. OK, so that's the solution. But this is, so you could say, let's take that for all into a for most and see if we characterize the same family of functions. And we don't, because here, if you pick a random x and test that p of x equals p of x plus 1, that will pass good programs. Oh, that's just that's a comma. Where? Ah, yeah, OK, yeah, thank you. Thanks, yeah, so it's, yeah, it's f of x, sorry, it should be f of x plus 1 equals f of x. OK, thanks. OK, and also I'm missing it here, the same thing. OK, thank you. Good. OK, so good. So so nothing passes this the way I've written it. Thanks for the, OK, so that should be a plus 1. So I told you this is a comedy of errors, and I told you there would be errors on the slide, and it's good some of you are awake. OK, so good programs pass the corrected version of this. Bad programs also pass, because what if you had the function f of x equals x mod n over 2? OK, so it's looking good for a while. F of, you know, everything's great. There's only one place where you're not going to pass that, and that's when you f of x equals x mod n over 2, where is that? Right exactly at n over 2 minus 1. And then you're going to have a huge slope. All the rest of the time, your slope is going to be 1, and the neighbors are just going to differ by 1. So that's, right? So this is a terrible functional equation. And in particular, you can prove a lemma that says that anytime you have a functional equation that's defined by the function at x and other linear functions of x, like 2x, 4x plus 3, no matter how many of them you use, it's going to be a constant number. But you will have a bad tester. There will be a bad program that will pass this test. Okay? And you use, essentially what you show is underneath the relationships, there has to be a nice expander graph. And Maria Klaue had this theorem that showed that if you define a graph via linear functions, it cannot be an expander. Okay? So for example, here's something I found in the literature. It was somebody named Cody used this functional equation to test the real gamma function program that he had. And this means that we can come up with a bad example that would pass his test, but it's a bad program. Okay, this compares 2x, x, and x plus a half. OK. Now, Weinstein, there was a guy named Weinstein that had this really, he had this cool theorem that said, so it was known that it was known which functions have addition theorems. So there's all these, it's a pretty big class of functions. Algebraic functions of periodic functions, algebraic functions of doubly periodic functions. These all have addition theorems. And Weinstein said you can even find it algorithmically. And it turns out you can use the nice ones to test. What does nice mean? It means you can solve for one of x, x plus x, y, or x plus y in the equation of the functional equation. So as long as you can get one on the left side in terms of the others on the right side, then you can use it to test. Good. OK. All right. So what other functional equations are robust? This is a pretty wide open area. There's a lot of open questions here. Just take the books, open to a random page, and you've got a problem. Okay? So there's much more that's been done on testing. I'm not going to talk too much about it. There's been polynomial degree testing, locally testable codes, improved linearity tests, a whole big field of property testing for testing graphs, strings, matrices, all kinds of things, okay? So but I want to talk a little bit about testing with a prover. Okay, so in particular, I want to talk about a work in '99 on approximate interactive proofs in PCPs for problems in P. I want to apologize because I'm going to mix the models of interactive proofs and PCPs. I'm not going to worry about space bounds, and I'm not going to worry about anything. Okay, so but I'm just going to talk. Okay, so here was the example we used back then because this was this was during the internet craze. So there were all these startups, and they were doing, everybody was caring about clicks, and back then, and they didn't have the fancy cryptography we have now to do things, and we have a lot of new methods. But what if I just wanted to prove that I have a popular website, and I want to show you, look, I've had all these hits, and I have a huge number, let's say millions and millions of hits, and I have this huge list, and you're like, okay, but you could have cheated because maybe half of those are fake entries, or maybe they're all duplicates. So, you could ensure that I didn't cheat too badly by taking some random sample of the entries and actually going to check and see, did those people really hit my website? Maybe there's some way to do that, some kind of hire a private detective and have them do it. So that may be a way you could do it. And how would you ensure that I didn't put in a whole bunch of duplicates? Well, there's so many lower bound protocols. Even Goldwasser, Sipser, or something like that, you could use to show a lower bound on the size of the set, to show that I don't have that many duplicates in there. Okay, so this is something you could do. And I want to mention an application of this idea of showing lower bounds on set sizes. Okay, so let's say I want to prove to you that a graph has a large size. Let's say I'm a client, I have a large graph, and I want somebody to find me a large cut. The program says there's a cut of size at least k. I want the money, okay? All right, so I would be happy to pay them if there really was a cut of size at least k, but I don't know, maybe they're cheating me. Okay, why should I believe you? Well, the program says here's a proof that you can check in constant time that there's a large cut in the graph. And I'm not gonna know at the end that there's a cut of size at least k, but what I will know is there's a cut of size at least k times 1 minus epsilon. Okay, so it's an approximate PCP, it's not a good PCP. Okay, so for each node, here's the proof. This is going to be written down like a PCP. So for each node, and this is simple, okay? You don't need to know anything to follow this. Okay, for each node, we're just going to write down its color. Is it on the red side or the blue side? Okay, so just an array of size n. And then a list of k edges crossing the cut. Okay, so that's what they'll write down for me. And now what do I need to check? Well, I need to check that these entries are legal. Like, it could be that some of these entries are illegal. So what would I do? Well, I could go to node 42 and 47, check their colors, and make sure that one is red and one is blue. And I could also check that they appear in the original graph, that it's a real edge. Okay, so it's constant time to check if a node is legal. And then we could check if the entries are distinct. Again, using the previous page. Is that a question or a? Oh, okay, that's okay. Sorry. All right. Okay. So what we can get is a protocol that if the cut is size k, then the verifier is going to pass this protocol. And if the cut size is less than 1 minus epsilon times k, then the verifier is going to fail. And it's constant time. Okay. What about something like bin packing? Here you have n objects of x1 through xn, bin size b, integer k. And here's a log n time protocol such that if all the items fit in at most k bins, then the verifier is going to pass. And if at most 1 minus epsilon fraction of the items are simultaneously packable, then no matter how the proof is written, the verifier is going to fail the proof with probability at least 2/3. Okay, so what we'll represent here, we're just going to write down something, again, really simple. No encodings, nothing. Okay? Well, maybe, but we'll start this way. Okay, so for each bin, it's of size b. We're just going to write down an array of size b with the name of the element occupying that space. Okay, so it's going to look like that. So here, 1 got these locations in the bin, 2 got 2 locations in the bin, 2, maybe item 2 is of size 2, so it gets 2 locations. Item 3 is of size 6, so it's going to get 6 locations in the bin. for each element, we write down its name that many times, the weight of the item many times, to show what space it got. And then what we're going to do is define a good item so that we can test, so that once we believe an item is good, we know all the good items are simultaneously packable. So this is, like, we have to be creative how we make this definition, but we have to ensure that if these things are all good according to this definition of good, they will be simultaneously packable, and we have to come up with a notion of goodness that can be tested quickly. Okay? And then if we can do this, then we're going to randomly sample the items. We're going to test that they're good, okay? So we're going to take a random sample of items, test that they're good, then ensure that most items are good, and if they're mostly good, then they're all simultaneous. Then by this theorem that we'd have to prove, they would be simultaneously packable, and then we can say, okay, good, most of these items are simultaneously packable, and so there's a, so it's okay to pass. All right? So what would this look like? Okay. I think I'm there. Okay, so this is one possibility. We could write down for each item, like the locations in the bin that it contains, and then the verifier could go and check, okay, if item 3 is of weight 6, I can go and check that it was actually allocated 6 locations, and I know it's everybody that's in there is simultaneously packable. It's good if it really was allocated 6 locations. 4 was allocated 1 location, and if that's its weight, then it's good. This is great. But then we have to go and check, the checking time of the verifier to check that an item is good depends on the weight of the element. So I have to go and check every location. And if you don't check every location, like 6 has all these locations, if I get tired and say, okay, it looks good, I'm going to stop now, then somebody could have thrown in a 7 in there without me realizing, and then maybe convinced me that 7 is good as well as 6. And I wouldn't have noticed that 7 got snuck in there. So I really have to look at every location. Okay? So luckily not, we can use ideas from monotonicity testing so that you really only need to do logarithmic time to sample this. I'm not going to show you why because I'm running out of time. Also because I didn't make the slide. So I just want to say there's a lot of other problems you can solve with these kinds of approximate PCPs. Again, it's approximate PCPs. It's not giving you the real answer. But you can do constraint satisfaction problems. There's a bunch of them. All kinds of packing problems, positive linear programming problems, set maintenance, property testing kinds of questions, and so on. Okay. So I just want to say more on testing with a prover. There's a lot, and people are going to talk about it. I think there's lots and lots more. So I'll just leave it at that. I just also want to mention that there's different approaches. So everything I've talked about in this talk went really problem by problem. Each problem we tried to solve separately. Maybe there was some kind of general tools and techniques that we could use between problems. But there's another method of approaching these questions. It's more class-based, like a method for all functions in a complexity class. And I'm going to call this the P revolution, okay? And P stands for polynomial time, not, okay? So, and in checking, it doesn't stand for parallel, okay? All right, so in checking, for example, there are parallel checkers in constant depth by Goldwasser, Gutfreund, Healy, Kaufman, and Rothblum. They do something really cool. They delegate the work of the checker to the untrusted program, and then the checker doesn't have to do that much. Even if it doesn't trust the program, it can check those parts of the program. And there's even new work that I think is yet to come to deal with fine grain. Remember before I told you with the little o property that people didn't like it because we didn't have fine grain complexity back then. So this really is a good time to revisit all those definitions and come back to this. And I think, and it looks like somebody's already started on this good idea. So great. And then interactive proofs for muggles. These are interactive proofs for all problems in P. It deals with a whole class of problems. There's lots and lots more since then. Come to the talks tomorrow. In fact, you'll fall in love with it. And so that's want to say. I want to mention there's more been done on self-correction, but I'm not going to talk about that either. Locally correctable codes, sampling correctors, local property reconstruction. Another talk. Concluding remarks. The typical advice to a graduate student is usually you should work on the hard, important problems. And maybe you should. I don't want to tell you not to, but I just want to say sometimes bumbling around on a random walk can be fun. Okay, and actually some people in this room have even proved that random walks can get you good results. So maybe we should trust them. Okay, and that's it. Thank you. And one more error. So that's actually what I looked like back then. So it's